Okay, so welcome to this neuroscience session number 2. And there will be 4 presentations. And since I am also presenting, I invite Dr. Skaper to help me in running this session. And I have my pleasure to invite the first speaker, Professor Skaper, to speak on protein transduction domain fusion, proteins as a therapeutic for neurological disorders. Please.
Okay, we'll start by thanking the organizers for having me this chance to speak at the meeting and to visit once again Vienna. The talk I'm going to divide into 2 parts, dealing with, still I can see my slides from here, protein transduction domain methodology applied to problems in the neurosciences. The first part will be devoted to neurotrophic factors and how to get them into the brain. Let's see. Okay, if you look in the developing peripheral nervous system, at the time when neurons are projecting to their target territories, for example, spinal ganglion sensory neurons, many of those neurons in the adult will not survive, which is believed to be a sort of competition for a limited amount of survival support. So in a sense, nature has given us a way to produce the right number of neurons, not too many, not too few. Now, this concept, what has become called the neurotrophic hypothesis, was shown very elegantly by Hammer and Montalcini back in the 1940s. So what they did was to take chicken embryos and the spinal ganglion neurons, which project to the limb bud. If you take and remove the limb bud, all those neurons would die. If you would graft on an extra limb bud, more neurons would survive that would normally do so. So what they hypothesized was that the target tissue was producing something, factor or factors, taken up by the nerve terminals, which supported survival of these cells. And these were sort of classical experiments in neurobiology, way back when in the 1940s. So Rita Montalcini with Stanley Cohen and St. Louis, some years later, were eventually able to identify and isolate the protein responsible for this survival effect, which we now know as neurotrophic factor. And as it turns out, that was just the tip of the iceberg. There's a whole family of these factors which promote neuron survival. And in fact, in 1986, Cohen and Montalcini received the Nobel Prize for the discovery of NGF. So basically, in the PNS, this concept is quite straightforward. These cells neurons project to the periphery, their target, they take up this trophic support. If you deprive them of that, they die. Okay. It applies also in the CNS with some variation. Neurons in the basal forebrain, which are cholinergic, project to the hippocampus, which produces NGF. If you cut this projection called the fornix, these neurons in the basal forebrain will die. However, unlike the periphery, CNS neurons, some of them, also produce neurotrophins and respond to them. Could have also autocrine and paracrine effects, in addition to their deriving support from the target. Now, these cells, so people thought, well, okay, so if you cut that and these cholinergic neurons die, what happens if can you give NGF in the lesion and save them from dying? In fact, you can, First papers came out in 1986, showing that if you infuse NGF into the basal forebrain following transfection, you, in essence, rescue these cells. Now, what happened was they were looking at staining of choline-astrotransferase from cat at 2 weeks, and what happened was really wasn't a death of cells, it was downregulation of phenotype. So looking at NGF, the cat was re-expressed. If you wait longer, these cells will actually eventually die. Now, these are the same cells, cholinergic cells, which are lost in Alzheimer's disease. So people thought, well, perhaps Alzheimer's disease is related to a defect or deficiency in NGF signaling. So this gave her the idea of using NGF perhaps as a therapeutic. Now, of course, in the human brain, inserting a cannula, as in the rat, is not as easy. The distance is quite a bit greater anatomically. There were studies done some years ago. A few patients were infused with NGF, and apparently there was a beneficial effect, although that didn't progress. It's not practical, really, to do this on a large-scale basis in man. But the idea of using neurotropic factors as a therapeutic has still garnered much interest. Also in the case of Parkinson's disease, in which the dopaminergic neurons, which are lost, are responsive to other neurotrophins, not NGF, but for example, brain-derived neurotrophic factor, which is within the NGF family of neurotrophins. But I think the problem is how to get the neurotrophin into the site where you want to rescue the affected neurons. So of course, getting these proteins across the blood-brain barrier is quite a challenge, and getting them across the cells, being proteinaceous, the cell membrane is really not very user-friendly to transport proteins. So people thought of other strategies. If you understand how these factors signal, you might be able to design medics and small molecule ligands do the same thing. So, as I mentioned, NGF is the prototype of this family of neurotrophins. Later, people discovered BDNF, derived neurotrophic factor, neurotrophin 3, neurotrophin 4. NT45 is the human analog of NT4. There's also NT6 in fish, which we won't talk about. So, actually, the first, these neurotrophins bind to receptors called TRACs, tropomyosin receptor kinase, which has a tyrosine kinase signaling motif in the cytoplasm. When the factor binds actually dimers, like other growth factors, leads to activation of this kinase domain and a signaling cascade inside the cells. Before the TRACs were discovered, people found this protein called P75. It was first described as the low-affinity NGF receptor. However, P75 is now called the P75 neurotrophin receptor because it binds all neurotrophins with equal affinity, low affinity, nanomolar affinity, whereas the TRACs bind with picomolar affinity. And the binding of the TRACs requires dimerization. And dimerization, like with other growth factors, FGF and EGF, leads to activation of a signaling cascade, another complex, and induction of gene transcription genes which are involved in survival and differentiation and outgrowth. P75 does not have an equivalent kinase signaling domain. It was thought just to be an accessory binding protein. As it happens, P75 is part of a more complex process in which it's, when it's not engaged with NGF, it becomes pro-apoptotic. Now, having worked out the structures of the neurotrophins and the binding sites of the given molecules, there's been quite a bit of activity in the design of mimetics and ligands to activate the TRACs and replace the intact protein. Generally, if you design a monomeric cyclic peptide, it acts as an antagonist. If you design a dimeric peptide, either tandem, repeat, or cyclic, these generally act as agonists. People also have designed small molecule non-peptide agonists, and these are intended to bind. It's complicated because you, unlike the mature neurotrophin, which has to bind both faces of two tracks and create dimerization, the challenge is to get a small molecule which will engage the binding domains of two tracks and dimerize them and transmit a signal. So there are these molecules which do mimic the native neurotrophin. They activate tracks that cause phosphorylation. They stimulate right outgrowth. They promote neuron survival. The affinity is generally much lower than for the mature protein. Some of these do have effects also in vivo. This one peptide called LM22A was used in a model of Huntington's disease. There are a number of these. Huntington's disease is caused by mutation in the protein Huntington. It's a disease involving polyglutamine repeats. When you have a chain of polyglutamines that exceed 20 or so amino acids, you get pathology. The more polyglutamines, up to 100 or so, the more rapid is onset of the disease and the more severe is the disease. So these authors took this mimetic and applied it to these animals. If you look at the medium spiny neurons and striatum, which are those affected in Huntington's disease, these spines on dendrites don't mature very well. This is wild type, this is the mutant. When they gave this mimetic of the tract B, they had good preservation of these spines on the dendrites. There is some thought that BDNF deficiency might be involved in Huntington's disease. In fact, BDNF, given locally, is also effective in alleviating some of the neurological consequences of the disease in these Huntington's animals. Spines are important because these are contact points in symptom transmission and also an element of long-term potentiation. Now, another way of mimicking neurotropic factors, well, if we go back, the idea of giving the intact protein, so how to use the intact protein and not the synthetics, how do you get it across the blood-brain barrier? Well, one can think of these Trojan proteins. One example is to take, for example, BDNF and hook it up to transfer. Now, endothelial cells in the blood-brain barrier have transfer receptors. So if you hook up transfer to BDNF, in effect, you can get the fusion protein to bind to the transfer receptors in the blood-brain barrier and get the BDNF across the blood-brain barrier and be effective in pathology. But again, this has its problems. So one way also is to use what are called protein transduction domains. This is antigen peptide is one. Another one used very often is the tag sequence derived from the HIV virus, the code protein. So what you can do is essentially take your cargo protein, stick on the TAT, and this undergoes this macropinocytosis where it binds to the cell, gets inside very rapidly. These proteins with TAT attached will get across in just a matter of minutes inside the cell. So there is precedent for this. For example, BCL-XL is a anti-apoptotic protein. The intact BCL fusion protein is neuroprotective in brain function. JUNK is activated in many of these pathologies in ischemic brain. JUNK inhibitors are neuroprotective, and this cathepsin, the JUNK inhibitor, was protective against melanine-induced produced destroyed brain lesions, another model of Huntington's disease. Glial cell-derived neurotrophic factor, another neurotrophin not related to the NGF family, linked up with TAT, has been used again as in brain infarction models. It's neuroprotective, protects retinal ganglion cells after axonomy. So this technology has been proven to be effective in getting particular molecules at the site of entry and across the blood-brain barrier. So we tried this with a protein called CNTF, ciliary neurotrophic factor. CNTF is not really classified as a neurotrophin. It's been classified more as a neurokine, sort of a cross between a neurotrophic factor and a cytokine. It's expressed in Schwann cells and astrocytes. It is neuroprotective, supports survival of motor neurons, sensory neurons, and cerebral and hippocampal neurons. It's a bit different from neurotrophic factors like NGF. It's not normally secreted like FGF. It doesn't have a single peptide sequence. It doesn't normally circulate in the body, which is probably good. I'll tell you why. It's produced in small amounts following lesion. Now, the reason it's called a neurokine is because apart from its own receptor, CNTF receptor alpha, which does not have a signaling motif, it signals through a complex which includes GP130 and LIF receptor, beta LIF, leukemia inhibitory factor, is a pro-inflammatory neurokine. GP130 is a signaling molecule which works together with interleukin 6 receptor. Interleukin 6 is a pro-inflammatory cytokine. So in essence, the risk is that CNTF does not circulate because CNTF potentially could cause inflammatory reactions. Now, ironically, given that CNTF is active on motor neurons, it is effective in animal models of motor neuron disease, ALS, multiple sclerosis. Clinical studies were undertaken in patients with ALS to see if it would be effective as a therapeutic. Now, one might predict, knowing how it signals and its potential for being inflammatory, that you might promote an adverse reaction in man. In fact, when they infused NGF into the ALS patients, the results were totally disastrous. The patients suffered exit wasting and all sorts of negative inflammatory reactions, which is probably predictable based upon the way CNTF signals. It's interesting that the company which developed CNTF for this indication, and given its effects on weight loss, are now developing CNTF mimetics as therapeutics for anti-obesity to promote weight loss. So what we did was to make a TAT CNTF fusion protein and see if this would behave more favorably than CNTF. So when you do this, you ask, well, is TAT CNTF active biologically? In fact, it is. If you take, these are neurons from sensory ganglia, which respond to NGF and also at this age to CNTF. These are, like I said, control NGF, produce a very nice neuron outgrowth. This is recombinant human CNTF. This is the TAT CNTF protein. So it does not lose biological activity. In fact, if you titrate it, the TAT CNTF protein, fusion protein, is as potent as recombinant human CNTF and NGF. The fusion protein, CNTF fusion protein, is also activated and produces phosphorylation of STAT3, which is a transducer and activator of transcription 3 in these neuroblastoma cells, as well as CNTF. STAT activation is part of the signaling cascade of CNTF, which is quite different from the neurotrophins. So as a model in vivo, we chose the synthetic nerve lesion in rats together with this group in Brazil. And what you do is take rats at 2 days of age, transect the synthetic nerve, and look at survival of motor neurons between days 2 and 7. So if you infuse either in CTF or the TET CTF, either locally or subcutaneously, you get a rescue of motor neurons. The scale's been cut off, so we take one as the control. You lose over the 7 days about 50% of the motor neurons. There is rescue with both CTF and TET CTF, given either locally the site of the lesion or given subcutaneously. It looks like the TET CTF is a bit more active in lower concentrations than the CTF, but both are active. So you might ask, well, both are active, so why do you bother making a fusion protein when CTF is just as good as the CTF itself? Well, as it happens, as you might expect, the CTF does affect body weight. So this is the CTF over the 5 days administration in these rat pots. They don't gain weight as do those with the TET CTF. So as a man, the CTF does affect the weight in the animals, which is not desirable. So we've lost an effect. We take biological activity, but lost the effect by making a fusion protein. The other thing you don't see is that the CTF induces fat mobilization in adipose tissue, unlike the TET CTF, which is also desirable. So by using the fusion protein, we have gotten around these adverse effects of the CTF. So just quickly summarize this. CTF fused to TET sequence is active biologically. It doesn't have adverse effects of fat mobilization. It doesn't cause body weight reduction. It doesn't, CTF also, we were seeing an antibody response in these rat models, which you don't see using the TET CTF. Why this is, we don't know, perhaps because of the very rapid uptake of the CTF into the cells, or the way it signals cytoplasmically. Now, the last part of the talk, going to show the application of the TET technology, which deals with a protein called alpha-synuclein. Alpha-synuclein is a presynaptic protein. It's found throughout the CNS. It has various roles physiologically in alpha plasticity, secretory granule vesicle production, regulating dopaminergic neurotransmission, but it is also involved in neuropathology. You see evidence of alpha-synuclein in Parkinson's disease called Lewy bodies and Lewy neurites. You see evidence of synuclein in multiple system atrophy, in oligodendrocytes, and also in other brain disorders. For example, Parkinson's disease with dementia, Down syndrome, and also what's called dementia with Lewy body. So this evidence of alpha-synuclein are pathological. And in fact, it's been used to produce models of Parkinson's disease. What people have done is to engineer mice genetically to overexpress alpha-synuclein, and you can do this. There are mutations of alpha-synuclein which promote aggregate prone. These animals produce aggregates, they produce PD pathology. The problem is it's difficult to control the amount of synuclein production in these animals. So we thought, could we take and have something more controlled, where we actually inject synuclein into the affected brain area called the substantia nigra, which contains the dopaminergic neurons lost in Parkinson's disease and produced in Parkinson's disease-like pathology. What are more controlled conditions? The problem is that if you inject alpha-synuclein into the substantia nigra, it doesn't get inside the cells. So, a classical model of Parkinson's disease is to inject stereotaxically into the substantia nigra 6-hydroxydopamine. So we use that as our standard. or this fusion protein TAP linked to alpha-synuclein, this mutation, which is more aggregates prone. So if you do this and look at staining in the substantia nigra for tyrosine hydroxylase, after 3 days you see loss of cell bodies by missile stain and loss also of TH staining. About 30% of cells are lost after 3 days. It's quite a rapid cell loss. So then we took these animals and looked at their behavior. This is called the rotaron, a classical example in which you put, these were rats by the way, not mice, on this device, and you can turn at various speeds and see how long it takes for them to fall off. So when they become neurologically impaired, they fall off more quickly at lower speeds. So we injected 6-hydroxydopamine and did the test after 30 days, or injecting the 10 alpha-synuclein fusion protein, and tested after various times. So we set a time limit in different speeds, increasing speed until the animals fell off. Did this daily for 5 days and compared the effects of this neurotoxin with our fusion protein injection. So this is what happens when you inject 6-hydroxydopamine. Animals become, after 30 days, impaired compared to the controls. If you look at the ones with alpha-synuclein, TET protein, they also develop neuropathology, but more slowly. This is after 15 days, 30 days, and 90 days. So the effect, even though we have a loss of dopaminergic cells after already 3 days, very quick, and no more, the pathology neurologically develops much more slowly, which is more akin to what you see in Parkinson's disease. L-DOPA is sort of the gold standard therapy for Parkinson's disease, at least early on in the disease. So this again is our control. This is the effect of the 6-hydroxydopamine and the rescue, the rotaron test of L-DOPA given in these animals with 6-OHTA. Again, you do the same thing with the 10 alpha-synuclein. The reduction pathology which you see is recovered, treated with the L-DOPA. So, in conclusion, with this part of the talk, that you can attack alpha-synuclein fusion protein given intranasally produces a very rapid and partial loss of dopaminergic neurons. When we get a neurological dysfunction or impairment, which occurs slowly with time, unlike the 6-hydroxydopamine, the effect is delayed following loss of neurons. And you can reverse this with L-DOPA as with the 6-hydroxydopamine model. So we think this actually is a better model than 6-hydroxydopamine for testing neuroprotective agents, which is something we are now looking